Today we're going to talk about relationship databases, like MySQL, PostgreSQL.
Hmm?
Things every, vibe coder should probably know. Okay, let's maybe unpack this a bit. Relational databases, well, at their core, they're really about structuring information efficiently. Think of it like, I don't know, organizing a massive library. You don't just dump books everywhere.
Right, you need sections, a system.
Exactly. So in databases, the sections are tables, holding data in rows and columns. And how they relate, well, that's the catalog.
And the language for all this.
That's SQL. Structured query language?
Yes.
That's how we, talk to the database?
Precisely. And these relationships, they aren't just like abstract links. They actually mirror real-world stuff, dependencies.
Like what?
Well, think about a blog post. It has comments, right? Or an e-commerce site, a customer places orders.
Okay, yeah.
Those are natural relationships. And structuring the data like that just makes everything, well, more manageable. Fewer errors, too. And the really neat part is the mechanism we use. Primary and foreign keys. That's how we define and enforce these links.
Okay, primary and foreign keys. Yeah, they sound a little technical, maybe a bit like jargon. But they're really the foundation, aren't they? A primary key is kind of like the unique ID, the DNA for each record in a table. Guarantees no two are the same.
Exactly. And the foreign key.
That's the link, right? It establishes that connection between different tables.
Yeah.
Like a reference in one table pointing to that unique ID, that primary key, in another.
That's a great way to think about it. And, understanding this stuff isn't just for database admins.
Oh, definitely not.
If you're building pretty much any app that saves data, or if you're analyzing data sets, well, getting how these relationships work, how these keys function, it's fundamental.
Yeah.
It's the difference between like a solid system and one that feels like it's held together with digital duct tape.
Absolutely. So to really get our heads around this, we've got a couple of really good sources for this deep dive. First up, there's this great article from DV Community. It's called Mastering Table Relationships in Relational Databases, the Role of Primary and Foreign Keys. Should give us a solid base.
Sounds good.
Then, to see how it all works in practice, we'll look at the Wikipedia entries for two big players, MySQL and PostgreSQL.
Perfect. So our mission today is basically to break down how tables connect in these relational databases.
Right.
We're really going to focus on primary and foreign keys, what they are, what they do, why they're so important.
And we'll touch on MySQL and PostgreSQL too, see what they bring to the table.
Exactly. So let's start with the absolute basics, table relationships themselves.
Okay, so first question. Why even bother setting up these relationships? Why not just, chuck everything into one massive table? Seems simpler, maybe?
Well, it might seem simpler at first glance, but trust me, that approach gets messy really, really fast.
How so?
Imagine trying to track customers, their addresses, and every single order they've ever placed, all in one giant spreadsheet.
Oh, okay, yeah. Nightmare.
You'd have the same customer details repeated over and over and over again with each order. Think of the wasted space. And updating info, forget about it.
Right, update an address in one place, miss it in 10 others.
Exactly. So relationships let us store each piece of info just once, customer details in a customer table, orders in an order table, then we link them.
Save space, makes updates easier, less chance of inconsistent data.
Precisely. It's all about organizing for efficiency and, importantly, accuracy, reflecting those real-world links.
Makes total sense. A customer has many orders. A student takes many courses. And the keys, primary and foreign, make those links explicit. Okay, let's dive into primary keys first, the unique identifiers.
Right. So a primary key, like we said, is all about making sure every single row in a table can be uniquely identified. It's a column, or sometimes a set of columns.
A composite key.
Exactly, a composite key, whose combined value makes that record totally distinct from all the others. Think of it like a passport number uniquely yours.
Got it. So what are the absolute must-haves for a primary key? What makes it work properly?
Okay, several critical things. First, uniqueness. Obvious, maybe, but vital. Every value in that primary key column or the combination for a composite key must be unique. No duplicates allowed.
Okay, unique. What else?
Second, non-nullability. A primary key column cannot, under any circumstances, be empty or null. Every single record needs that identifier. It has to be there.
Unique and always present. Got it.
Third, and this is more of a best practice for stability consistency, ideally, primary key values shouldn't change.
Why not?
Because changing a primary key can cause havoc. You'd potentially have to update foreign keys pointing to it in other tables. It's messy and risky, so keep them stable.
Okay, unique, never null, and ideally unchanging. Anything else going on behind the scenes?
Yes, and this is huge for performance
Okay.
indexing. When you declare a primary key, pretty much any database system will automatically build an index on it.
An index, like in the back of a book.
Exactly like that. Instead of reading the whole book, you check the index, find the page number. Same idea. The primary key index lets the database find a specific row incredibly quickly using its key value.
Ah, so it makes lookups super fast.
Super fast. It dramatically speeds up data retrieval. Under the hood, they often use structures like B trees, which are really efficient even for massive tables. Logarithmic time, basically.
Logarithmic time, meaning it doesn't slow down much even as the table gets huge.
Precisely. So it's not just a unique label, it's an efficiently searchable unique label. Makes a massive difference.
Okay, that's clear. We've got unique identities sorted with primary keys. Now, how do we build those bridges, those links between tables? Foreign keys, that's their job, right?
Exactly. A foreign key is a column, or again, maybe a set of columns, in one table. Let's call it the child table.
Okay.
That points back to, or references, the primary key of another table, the parent table. Its main job is to establish and, crucially, enforce those connections. It ensures data integrity across your related tables. It's like a rule saying, hey, the value here must match a valid primary key over in that other table.
So back to our customers and orders example. The orders table would have a customered column.
Yep.
And that customered would be a foreign key, and every value in it has to match a customered that actually exists in the customer's table's primary key column.
You got it. And that's how foreign keys maintain referential integrity. The database literally stops you from creating an order linked to a customer who doesn't exist.
Prevents invalid links.
And it also helps stop orphaned records like orders floating around with no customer attached anymore. Keeps the data clean.
That sounds like a really important safety net for data quality. Now, the article mentioned one-to-many relationships as being super common. Why is that pattern so widespread?
Well, the one-to-many relationship just naturally models tons of real-world situations. Like we said, one customer, many orders. Or think about one author writing multiple books, one department having many employees. It's everywhere.
Okay.
And the structure is efficient. You store the one-side info, customer, author, department, just once. Then you link all the many-side instances, orders, books, employees, back to it using that foreign key. Avoids repeating data all over the place.
Makes sense. Keeps things tidy. So, one-to-many, one customer, many orders. The customered foreign key in orders makes the link.
Got it. Now, you mentioned cascading actions earlier. What are those about?
Ah, right. Cascading actions define what the database should automatically do to related records if something happens to the primary key they reference.
Like if you delete a customer.
Exactly. Say you delete a customer record from the customer's table. You could set up a cascade delete rule on the foreign key in the orders table.
And that would
Automatically delete all the orders associated with that customer. Poof. Gone.
Whoa. Okay, that sounds super convenient for cleaning things up,
Mm-hmm.
but maybe also a bit dangerous. Could wipe out a lot accidentally. Precisely. That's why you have to think really carefully about the business rules and the consequences before setting up cascades. It's powerful, but needs respect.
Are there other options besides just deleting everything?
Oh, yeah. You can have cascade update, so if you change a primary key value, which, again, usually not recommended, the foreign keys update automatically. Or you could set the foreign key to NLL, kind of unlinking the child records. Or you could just prevent the deletion of the parent record entirely if it still has linked child records.
Lots of options depending on what makes sense for the application.
Totally depends on your specific needs.
Right. Powerful tools, but plan carefully. Okay, fundamentals are looking good. Let's dig a bit more into the types of relationships. We've hammered one-to-many. What about one-to-one? When does that come up?
A one-to-one relationship is where one record in Table A corresponds to exactly one record in Table B and vice versa. It's less common than one-to-many, but useful.
Like when?
Often used when you want to split a table. Maybe some columns are accessed rarely or contain sensitive info, so you put them in a separate table.
It's example.
Okay, maybe a users table with just login stuff, username, password, hash, then a separate user details table with address, phone number, bio, stuff you don't need every time someone logs in.
Oh, okay.
Both tables would probably share the same primary key, say userid. And in the user details table, that userid would also be a foreign key pointing back to users, enforcing that strict one-to-one link.
So splitting one logical thing across two tables for performance or organization, but keeping them tightly linked.
You got it. Now, the other big one, many-to-many relationships. This is where things get a little more involved.
Okay, many to many. So one record in Table A can link to multiple records in Table B.
And conversely, one record in Table B can link to multiple records in Table A.
Right, gotcha. Give me a classic example.
Students and courses. One student enrolls in many courses, right? And
Right.
one course has many students enrolled in it.
Okay, yeah, perfect. Many to many. So how do you model that? You can't just put a course aid in the students table or a studented in the courses table.
Exactly. That wouldn't work. What you need is a third table, an intermediary table, often called a junction table or sometimes a linking table or join table.
Ah, the junction table. I've heard of those. It sits in the middle.
Precisely. It acts as the bridge. This junction table, let's call it enrollments, would have at least two columns. A foreign key referencing the students table's primary key, studented, and another foreign key referencing the courses table's primary key, course aid.
Okay.
Each row in this enrollments table represents one specific link. The student is enrolled in that course.
So one row might be studented, 123, course aid, CS 101. Another might be studented, 123, course aid, Math 200.
Exactly. And this table could also hold extra info about that specific relationship, like the grade the student got in that course or the enrollment date.
Right. So if I want to find all the courses student 123 is taking.
You look up studented 123 in the enrollments table, grab all the corresponding course aids, and then look those up in the courses table.
And vice versa to find all students in CS 101.
You've got it. The junction table effectively breaks down that complex many-to-many into two simpler one-to-many relationships. One student to many enrollments, one course to many enrollments.
It's actually a really elegant solution for those complex links.
Ooh.
Okay, awesome. Foundation laid. Now let's pivot to the big databases themselves,
Yeah.
MySQL and PostgreSQL. Let's start with MySQL. Wikipedia says it's, well, super popular. Open source RDBMS. What's the backstory?
Yeah, MySQL's history is pretty interesting. It came out of Sweden originally, a company called MySQL AB, founded by David Axmark, Alan Larson, and a Finnish developer, Michael Wadenius, often called Monty.
Oh, and Quiche, okay.
And the name apparently comes from Monty's daughter's name, and then SQL, first version popped up way back in like 1995.
Wow, that's ancient in tech years. And it started small, right? Based
Yeah.
on an older system.
Yeah, it was initially for personal use, built on an earlier database called MySQL. They found MySQL wasn't quite cutting it performance-wise, so they built their own SQL layer but kept a similar API.
Smart. Made it easier for people to switch.
Definitely helped adoption.
The entry also mentions this dual licensing thing, GPL and a commercial license. What's that about?
Right, the dual license gives options. The GPL, the GNU General Public License, means you can use, change, share MySQL freely as long as you follow the open source rules. Great for open source projects, developers.
What?
But if a company wants to bundle MySQL inside their own proprietary closed source product without releasing their code under GPL, they need to buy a commercial license from Oracle, who owns MySQL now.
Ah, so it serves both camps, open source and commercial. Now, speaking of Oracle, there was some big acquisitions. Sun Microsystems bought MySQL AB first.
Yep, Sun bought them in 2008. Then Oracle bought Sun in 2010.
And that caused some waves, didn't it? Led to MariaDB.
Big time. Monty Wadenius, the original creator, got worried about MySQL's future under Oracle. So he forked the code, took a snapshot of the open source version, and started MariaDB as a community-driven alternative. A lot of the original MySQL devs went with him.
So MariaDB is kind of like the spiritual successor in a way?
You could definitely say that. It aims to be a drop-in replacement for MySQL, often with more features or different performance characteristics. It's important context, for sure.
Definitely. Now, features-wise, by version 5.6, MySQL was looking pretty mature. ANSI, SQL compliance, cross-platform, stored procedures, triggers, views, and online DDL via InnoDB. That sounds solid.
It really was, and switching the default storage engine to InnoDB in version 5.5 was huge.
Why InnoDB specifically?
InnoDB brought robust transaction support that ACID stuff we'll talk more about, and crucially for our topic today, proper enforcement of foreign key constraints for referential integrity. Plus, online DDL meant you could change table structures, add columns, etc., without taking the whole database offline. Massive for uptime.
Essential for real-world apps. And later versions kept adding stuff, right? Like JSON support.
Oh yeah, JSON support, window functions, common table expressions, even some NoSQL-like features. It hasn't stood still.
It also mentions replication support. Asynchronous and semisynchronous. What's the difference there? Why choose one over the other?
Good question. Replication is about copying data to secondary servers for backup or load balancing. In asynchronous replication, the main server sends changes and just moves on, doesn't wait for confirmation.
Faster, but risky.
A bit. If the main server crashes right after sending, before the replica gets it, you might lose that last transaction. Semi-synchronous adds a check. The main server waits until at least one replica confirms it got the data before telling the application, okay, done.
So slightly slower maybe, but safer. Less risk of data loss.
Exactly. It's that classic trade-off. Speed versus stronger guarantees. Data durability.
Got it. A balancing act. Now, the entry does mention some, let's say, nuances or limitations, like maybe not 100% standard compliant always, and something about check constraints being late.
Yeah, that's fair. While MySQL aims for SQL compliance, historically, the level could depend a bit on which storage engine you used, though InnoDB is dominant now. And yes, sheet check constraints rules to limit what values can go in a column were a feature that Standard SQL had for ages, but MySQL only implemented them relatively recently. They relied on application logic for that before.
Interesting quirks. Okay, and deploying it seems straightforward. Manual installs, packages, cloud platforms.
Very flexible. You can build it from source, use package managers, or just spin up an instance on AWS, RDS, Azure, Google Cloud, Oracle Cloud. Super easy. Plus, tools like MySQL Workbench give you a nice graphical interface alongside the command line tools.
And loads of connectors for different programming languages.
Absolutely. Connector J for Java, Connector Net for .NET, ODBC, Python connectors. Pretty much anything you'd want to use, there's a way to talk to MySQL. And seeing active forks like MariaDB and Percona Server alongside the official releases.
Yeah, it shows a lively ecosystem.
Definitely. And it's still very much alive and kicking. The latest stable LTS release mentioned 8.4 from April 2025, and a preview of 9.3 shows they're still actively developing and innovating.
Cool. Okay, that's a good picture of MySQL. Let's switch gears to PostgreSQL, the other big open source contender. Wikipedia calls it an object relational system. What does the object part mean?
Good point. While both are relational, PostgreSQL leans more into object relational. It means it supports more complex data types like arrays and structure types, and features like table inheritance, which borrows concepts from object-oriented programming. It allows for more complex data modeling directly within the database.
Okay, so a bit more flexible with data types maybe.
Yeah.
And it's known for sticking close to SQL standards and being extensible.
Very much so. PostgreSQL has a strong reputation for SQL compliance, often being quicker to adopt new standard features. And extensibility is huge. You can add custom data types, functions, operators, even index types. Plus, it really emphasizes those ACID properties for transaction reliability.
ACID again. Atomicity, consistency, isolation, durability. The gold standard for transactions.
Absolutely fundamental.
And it seems to pack a lot in out of the box. Updatable views, materialized views, triggers, foreign keys, of course, stored procedures.
Yeah, it comes very feature complete. It also runs on pretty much any OS and scales really well to a single laptop up to massive distributed systems. Its roots go back even further than MySQL, actually, to the Ingress project at UC Berkeley in the 70s and 80s. The project was first called PostgR.
Wow, deep academic roots.
Very deep. The name changed to PostgreSQL in '96 to highlight its SQL support.
Now, one feature mentioned prominently is MVCC, multi-version concurrency control. That sounds important. How does it work?
MVCC is a really clever way to handle lots of users accessing the database at once, instead of using lots of locks that make processes wait for each other.
Which can slow things down.
Right. MVCC gives each transaction its own snapshot of the database as it existed when the transaction started. So reads don't block writes, and writes don't block reads. Everyone sees a consistent view without constantly waiting. It generally leads to much better performance under high concurrency.
That sounds significantly different from older locking models. Very efficient. What about storage and replication? Similar to MySQL.
It has built-in binary replication, and you can configure synchronous replication for higher durability. Similar concepts to MySQL, yeah. But where PostgreSQL often shines is its variety of indexing methods.
Beyond just the standard B-tree index used for primary keys.
Way beyond. It has B-trees, of course, but also hash indexes, gist, GN, SBG, gist, Brin.
Whoa, okay. What are gist and GN good for?
Gist generalized search tree is fantastic for indexing complex types, like geometric data for mapping applications or for implementing nearest neighbor searches. GN generalized inverted index is brilliant for data where one item might contain multiple keys, like full text search, indexing all the words in a document, or searching within arrays or JSON documents.
So you can pick specialized indexes to optimize very specific kinds of queries. That sounds powerful.
It's a huge part of PostgreSQL's flexibility and performance tuning capabilities.
The entry also mentions schemas. How are they different from just having separate databases?
Schemas are like namespaces within a single database. Think of it like folders inside a drive.
Yeah.
You can group related tables, views, functions together in a schema.
So you could have schema1.users and schema2.users in the same database.
Exactly. It helps organize complex databases, avoids naming collisions, and is great for managing permissions. You can grant access to a whole schema.
Ah, neat organizational tool. And user-defined objects, table inheritance. Sounds quite advanced.
It is. You can define your own data types, custom functions, operators, really tailor the database. Table inheritance lets one table inherit columns from another, like object-oriented classes, which can be useful for certain data models.
And foreign data wrappers, connecting to other systems.
Yeah, FTWs are super cool. They let PostgreSQL query data that lives outside PostgreSQL in another database like MySQL or Oracle in CSV files, even web services, as if it were a local table. Powerful for data integration.
Wow, like a universal data connector built in? That's impressive. And it seems it's widely used, too. Microsoft, Reddit, OpenAI, listed as users.
Yeah, its adoption is broad and deep across many industries and demanding use cases. That definitely speaks volumes about its reliability and performance. Tools like PSQL, the command line interface, and pgadmin, a popular graphical tool, make it manageable too.
And like MySQL, it's under very active development.
Absolutely. The versioning indicates continuous improvement, mentioning stable release 17.5, and beta 18 in May 2025 shows it's constantly evolving.
Wow. Okay, so both MySQL and PostgreSQL are clearly heavyweights.
Yeah.
Powerful, mature, feature-rich systems. It's really clear why they dominate the relational database landscape.
So just to wrap our heads around this, we've covered the absolute basics. Primary keys giving unique identity, foreign keys building the crucial links.
Enforcing that referential integrity. Right. And the different relationship types. One-to-one, the super common one-to-many, and the many-to-many needing that junction table.
Yep.
And then we got a good look at both MySQL and PostgreSQL, their histories, their core features, how they handle things like concurrency and replication, and their strengths.
That's a great summary. And honestly, getting a solid grasp on these relational concepts is just essential today. If you're working with data, designing schemas, writing queries, building apps, you need to understand how tables connect via keys. It's foundational.
Absolutely. So here's something for you, the listener, to maybe chew on. Think about your primary keys. Are you using simple auto-incrementing integers, UOADs? Maybe even composite keys. How does that choice impact performance? How does it affect how easily your database can scale, especially when the data starts piling up?
That's a great point. Or maybe think about the specific differences we touched on between MySQL and PostgreSQL. When might PostgreSQL's advanced indexing or extensibility be a killer feature for your project? When might MySQL's widespread familiarity or perhaps a specific feature offered by its ecosystem be the better choice? There's always more depth.
Definitely. The best way to learn more.
Dive into the docs. Check out the official documentation for both systems, but even better.
Get your hands dirty.
Exactly. Set them up, create some tables, define those primary and foreign keys, try building those relationships we talked about. Experimenting in your own projects is really the best way to make it all click.